All right, good morning, everyone. I have the top of the hour, and I want to welcome you to the NCAP from Research to Implementation webinar today. Our topic today is on high polymer modified asphalt mixtures. Very topical, really cool topic. We got some great presenters today as well. So with us, as always, is Nathan Moore. Nathan Moore is the Assistant Director for Test Track Research here with the National Center for Asphalt Technology. Prior to that, he was a research engineer in the laboratory, and he keeps really busy outside of work chasing his children, which are fantastic kids. And right now, he's on a national tour. So check your local agenda for your workshops and conferences because he's probably on that agenda. Next, we have Dr. Nam Tran. He's an associate director and research professor here at NCAT. For the nearly 2 decades, he's led influential research on pavement materials, performance testing, and design methods, working closely with DOTs, industry partners across the country. And similar to Nathan, Nam has three very active children, and he really loves being with them when he's not working. Dr. Johnny Haboush is a Western Regional Engineer with the Asphalt Institute, supporting agencies and industry partners across the Western U.S. Prior to being at AI, he was a senior research scientist with VTRC in Virginia, and he has authored over 85 technical publications. If Johnny seems like he's a little more energetic than everybody else today, that's because in his off time, he both participates and coaches in CrossFit. I do want to remind everybody, let's go ahead and keep yourselves muted during the presentations here. Any questions that you have, please type them in the chat box and we will wrap those up and answer questions after the presentations are done. Nathan, take it away.
Great. Can you hear me, Travis?
Yes, sir.
One thing you failed to mention is that you and Nam are actually twins born on the same day.
That's
So,
true. That's true. That's why we
although
got the same shirt on today.
that's exactly right. Although since Nam was born in Vietnam with the date line and all, I think he's probably older than you.
Yes, yes. And I take every opportunity I can to make sure people know that.
Can
That's
you tell
right.
us? Can you tell us the date?
No.
Why? Because I believe the three of us are born on the same day. But anyway,
Okay.
So yeah, welcome everybody. For those of you who may be new to this webinar, I just want to give you a brief overview of the format. You won't see me long. I'm the dumbest guy in the room here, and so I really want to. Yeah, I'm going to introduce the topic, and then give you just a brief overview of how we have utilized high polymer mixes at the test track. But then I want to kick it over to Nam as kind of our in-house expert on this, and then kick it over to Johnny after that. I'll come back at the end and we'll do questions and answers. I want to reiterate what Travis said. These webinars are only as successful and enjoyable as you guys are active. We absolutely love it when you guys get in the chat and go ahead and ask your questions. Feel free to do that throughout the webinar. Sometimes somebody would get in there and just go ahead and type in an answer. Other times it just spurs really good discussion at the end. So don't be bashful. Um, so high polymer modified mixes at NCAT, they really go all the way back to 2009 on the test track. And this is when Kraton sponsored the first high polymer test section at NCAT. And I'm pulling up this is an excerpt from the 2012 report where you see how the Kraton had over 10 million ESOL. It definitely it had the highest um, uh, strain response and the strain limit compared to lots of other different treatments. And this was, the original case where the polymer loading was 7 to 8%. Really, since then, I think this polymer loading has come down on a lot of these technologies, these high polymer modified mixes. Um, what's interesting is that this is one of NCAT's biggest success stories of partnering with private industry, because this was one of the very first like big projects that Kraton had actually used this technology on. I think they had, if I'm remembering correctly, they had put it on maybe some small commercial jobs, but this is an example of somebody really just believing in their product and moving forward. And now you look at it, and it's not just Kraton who's a player in this space. There's so like this technology has really exploded since then. So I'm looking forward to the content from today. Since 2009, I thought about putting a list together, but it just got too big. We have used the high polymer modified mixes a ton since 2009. Sometimes in rehabilitation, other times, in big group experiments to uh, prevent bottom-up fatigue cracking and force top-down cracking. Other times just to build perpetual pavements for surface evaluation and all kinds of stuff. So really, the usage of this technology is pretty prevalent at this point, and not even just at NCAT, really across the country. Some big lessons learned. What you'll find when you start using this material is watching your binder viscosity is critical. This stuff does tend to be stiffer than normal, so paying attention to that is really helpful. But the fact that the polymer loadings have come down just a little bit, it makes it easier to pump, and there's also a lot more technology that people who are smart about binder could tell you, to help it to make it easier to pump. Really, the big thing, though, in my opinion, I think one of the biggest lessons learned, and what we are trying to participate in the conversation to get the word out, is that these products, I mean, they significantly improve structural quality compared to conventional asphalt mixes. You don't need this stuff everywhere. But if you start to dig into the details about how these high polymer mixes work and how they impact structural coefficients or ME transfer functions, it's just quite remarkable. Here's uh, this is just a screenshot of the NCAT report 25-01, where Surrey Gadagante, Dave Tim, and Nam Tranan, and then one of their graduate students, Samina, wrote a report looking at structural layer coefficient recalibration using this product. So Nam's going to talk a lot more about this and some of the stuff that went into this report. So Nam, take it away. I'm going to turn it over to you.
Thank you very much for you know, filling the space for me is because for some reason I couldn't find the button to share my screen. And again, thank you all very much for joining the webinar today. And it is very really a pleasure and also an honor to talk with Johnny. He have done a lot of work in the area of the high polymer-modified asphalt. And in this presentation, I will focus on one thing, and the main question is how much high polymer-modified asphalt perform better than conventional degraded mix. And what I'm going to do is I will summarize the field performance on several experiments at the test track, and then I also look at the structure analysis for this experiment done by Dr. David Thiem and his group. And in the slide that maybe we can share later on, we also have some information about the life cycle assessment done by Dr. Gatiganti. But for the limit of time today, I'm not going to present that part. And last but not least, I have an example of field implementation done by Oklahoma DOT based on the test result from the test track that we have. So in summary, the goal for this presentation is to provide information for DOTs and other agencies to consider HPMA in structural payment design. And I know that Johnny probably will talk about the specification and current practice by DOT. So this would cover a full range of information that you may be interested in. So first, most agencies still use one structural layer coefficient for degraded asphalt. And when I say here is that we just make it simple for you to look at the structural coefficient, but the concept that we're doing here can be applicable to other design software or maybe procedure. For example, payment ME design, you can use that for perpetual payment design software, or you can even using the FlexPay with maybe more advanced analysis, and then the concept still the same. The only thing is that you would need different information for the input for the payment design. So the values is commonly about 0.44 in the ASTO 1993 approach, and this value is often applied to the same way for conventional and then also for polymer modified asphalt mixture. And another thing that very commonly used is that the polymer modification be used in the surface layers. And this has been the success for many decades. However, it's not common for using the polymer-modified asphalt in the base and the in intermediate layers. And then that it really create a gap between the current design practice and then the actual field performance of that mix. And then I'm going to talk more about that based on the experiment at the test track. So for the reason I stated before, the current payment design practice does not fully taking into account the HPMEA, the polymer modified asphalt performance. And the NK track section have shown better resistance to rutting and vertical cracking than conventional control section. And it was true even when the HPMA section was built thinner. But at the same time, if you do the maybe structure analysis and looking at the lab data, and if you consider the stiffness only, then the stiffness of the HPMA is not much different compared with the stiffness of maybe conventional polymer modified asphalt. So what what we would like to highlight here is that if you would like to have to take in the credit for the HPMA, you probably need a calibrated design coefficient or the way to take into account the HPMA resistant to cracking in the design procedure. So all of that lead to the main question for this presentation. Should HPMA mixture receive a higher structural layer coefficient, or should that section be built either thinner? And the answer is yes. And if that answer is yes, what evidence we have to support that maybe recommendation or suggestion? And again, the rest of the presentation will try to answer this question using the test track data, including using the maybe bending beam fatigue test in the lab, and then we also have an example of the implementation in the field for you. So the short answer to the question earlier is yes, you can build the section thinner and then you can apply a higher structural layer coefficient. And the number that I've shown here is that the layer coefficient typically we use maybe 0.44 in the 1993 payment design guide, or in the case of the Alabama DOT, they use 0.54 for the structural layer of the conventional asphalt mixture. Now, when we did all the analysis, and this is published in the NK report 25-01 that Nathan mentioned earlier, we found that the layer coefficient for HPMA can be as high as 0.92, and then the lowest, the number that we found would be 0.75. Now, why we have that two numbers, that is based on the conversion that we have using 0.44 for the conventional asphalt mixture or 0.54 for conventional asphalt mixture. I'll talk about that later on. But one thing that I would like to point out is that these values are based on several NCAT test track experiment, and then the combined traffic for those experiments is about 50 million ISO, starting from 2009 all the way to 2021. So there are 4 research and implementation efforts that I have in the set of slides, but what I'm going to go through would be the evidence number 1 would be the field performance on the test track. And then the next one here would be the structure analysis done by Dr. Tim and his group. And I will skip the life cycle assessment done by Dr. Gattiganti in that NCAT report 25-01. And I'll talk about the implementation example in Oklahoma. Okay, so the first thing is really the performance at the test track, and this part focus on what happened when the HPMA section was traffic under heavy truck loading at the NCAT test track, and then in the hot climate, and then we understand that the field performance is important because it links the mixture behavior and the actual pavement distress. So the first experiment that I'm going to present here is really the section N7 and section S9. So starting in 2009 experiment, and then this experiment is sponsored by Creighton at the time in 2009. So you can see here the section N7 was much thinner, that is 1.2 inch thinner than the control section with conventional polymer-modified asphalt, and then also unmodified asphalt in the cross section here. Section N9, 7 inch of asphalt, and then section N7 only 5 3/4 inch of asphalt. You can see here the another difference is that section N7 using HPMA binder, and then in this case it have about maybe 7.5% SBS in the order throughout the cross section, and then section S9 have a polymer modified surface and then the intermediate layer, but the base layer is unmodified asphalt. And then the base and then the subgrade are the same. Now, the next experiment is starting in 2010, and this start with back in 2006, Oklahoma DOT sponsored an experiment to look at whether the perpetual payment actually exists, or what is the value of the perpetual payment that can be built in Oklahoma. And then what we find out is that there are two sections, N8 and N9, but the section N8 start with 10 inch of asphalt on top of the steep subgrade that's stabilized material in Oklahoma on top of soft subgrade we bring in from Oklahoma. And the section N9 have 14 inch of asphalt is not showing here, but what we show here is that after 10 million ISO, section N8 with 10 inch of asphalt fail. And then Bush at that time decided that talk with Oklahoma DOT, and then they decide that they're going to mill the top 5 inches. That is typical of their rehabilitation strategies. And then we're also using the paving fabric in the interlayer there to see if we can prevent the failure. But fast forward only about 4.5 4.6 million ISOs, that section failed, and then we had to replace it. And then the idea come up with is that we have section N7 that perform very well, and maybe we just replicate that cross section on top of N8, and then it lasts to the end of the research cycle without any issue. And then you can see the picture on the right here that how that section failed after it was rehab with a mill and inlay of 5 inch on the top. So here's a quick summary of that two experiment on the test track. The first one is N7 from 2009 to 2015. This is very minimum rutting, and then same with the rehabilitation of N8 up to about 5.5, 5.6 million ISO, and then with very minimum rutting, and then the section still perform very well at the end of the research cycle at the time. Now, fast forward, and then after maybe the first research cycle, Creighton decide that they are going to fund the continue the traffic, and then so both section N7 and S9 will traffic up to 20 million ISO of very heavy truck traffic. And then what we find out is that you can see here the gray bar, the control, and then the orange bar, the HPMA. You can see in all the area that we monitor, the control section have more cracking. And then at the end, we also cut the core doing the forensic study. We found that section N9 had all bottom-up vertic cracking, and then we found no bottom-up vertic cracking in section N7, and it was concluded that the section N7 can be perpetual pavement with just only 5 1/4 inch of asphalt using HPMA in that experiment. Now, for the N8 section, after we rehab that section with the HPMA, you can see here Dr. Tim did all the testing and then conducting structural analysis with the strain gauge and then base pressure plate in the whole structure. You can see here the AC modulus, when you do the back calculation, increased by 40, 44, 45%, significantly increased. The asphalt strain at the bottom of the failed structure reduced by 20%, and then all the base plates, all the pressure plates made in the top of the base and the top subgrade reduced by 48 and 20%. So significantly improvement in the section N8. So the next section that I'm going to do here is that Dr. Tim looking at all the data, and then he also do the structure analysis, and then see how that section N7 perform compared with section N9 control. So you can see here in 2009 research cycle, we had section S9 with 7-inch of asphalt, and then section N7 with 5.5 3/4 inch of asphalt, which might be HPMA in that cross section. Now, what we find out is that the cracking resistance, or maybe the 30 line of that section, that one of the graph that Nathan showed earlier, that we determined that the predicted 30 life for that HPMA N7 section is 17 times greater than the predicted 30 life for the S9 cross section. You can see here the number that the strain gauge places at the bottom of the AC layer for N7 measure at 380 microstrain, and the S9 here at the 346 microstrain. And then we use that microstrain, put in bending beam fatigue test result, and then here's the number of cycles that last year was predicted based on that. You can see here 17 times greater. And then even though that N7 carry higher microstrain at the bottom of the AC layer, it still lasts longer. So fast forward to 2025, 2024, we went back to all the data for the TETRAC experiment. And then one of the question is, based on the TETRAC study, can we determine what would be the structure layer coefficient for HPMA mix? And then the analysis come out that yes, you can see here that the structure layer coefficient of the SPMA layer is almost double the typical value that have been used in the pavement design. Now, the analysis here is based on, we call it equivalent cross-section. What that means is that we are determining would be the 30 line for the cross-section of HPMA, and then make sure that the 30 line for HPMA cross-section will be equivalent to 30 lines, predicted 30 line for conventional section. In this case, that is a conventional make using maybe regular conventional polymer-modified asphalt. So if the layer coefficient for conventional make is 0.54, then the layer coefficient for SPMA will be 0.92. And then if the state using maybe the typical 1.44, in this case, HPMA makes would have the layer coefficient of 0.75. So the next one here that I would like to talk to is based on the success of the rehabilitation in section N8, Oklahoma DOT actually picked it up and put it in the use for their field project. So there's one section of I-40 in Caddo County in Oklahoma, and then you can see here the elite of rehab. So that section was built in 1962. It had been going through a lot of rehabilitation, and then it keep failing until 2012. Oklahoma DOT decided that they are going to do the major rehabilitation so that they don't have to repair that more. So here is the design for that experiment. They come in and then they mill 5-inch of HMA, but they are not milling the whole cross section, but they leave there about 4.5 inch of asphalt concrete, the board that have a lot of crack in there in place. And then you can see here on top of that, they put in 8-inch of HPMA mixture, and then it's very similar to the mix design that was placed at the test track. On top of that, they put OCFC layer in there. And then the construction was done from February to April in 2012. Fast forward 9 years later, you can see here is there a lot of truck traffic on the section up to 2021. The IAI for that section is still below 50 inch per mile with great performance. And then in 2022, the Asphalt Payment Alliance gives the perpetual payment award by conversions. And you can see here there are several pictures of that section in 2021. There's no cracking, and you can see here that there's reflective cracking on the shoulder using the conventional mix, and then that reflective cracking is stopped when it go into the HPMA mix. This one in this case is PZ76-28E, and then next to that is the perpetual payment award presented by API. So this will be the last slide for me. And you can see here that maybe this is just our recommend adoption or implementation pathway for these technologies. So in order for the state to justify the use of SPMA for the structural payment design, we believe that you should adopt a higher layer coefficient. And if you're in a state that using payment ME design, you need to do some fatigue cracking test, and that includes that cracking resistance into the payment ME design procedure. And then if you're using perpetual payment design, you can do the same, and then you can determine maybe we call it endurance limit when you design perpetual payment. So then the second step, it can be that because the section that you build with HPMA will be much thinner, and then you can, if you're not very comfortable with that at the beginning, you can select one or two pilot project, or you can talk with Nathan here, maybe do some very quick testing on the test track with accelerated payment testing, and then verify that the structure design would be sound and good for the state. And then last but not least here, based on the pilot project and then some of the testing throughout the pilot project, you can update the material specification and then also the payment design procedure in the state. And with that, I'm going to transfer to Johnny.
Well, good morning, everybody. And again, thank you to Travis, Nathan, and the NCAT team for this invitation. I'll be talking a little bit more about the state of practice of using high polymer modified asphalt mixtures, mainly in the United States. And what I'm going to present is an effort that was completed by the Asphalt Institute in collaboration with the Virginia Transportation Research Council, and that's under a cooperative agreement that the Federal Highway Administration has with the University of Nevada, Reno, to which AI, VTRC, even NCAT acts as subs and are working on great topics to deploy innovative technology. So it's a non-research contract. It's just mainly focused on deployment of innovative technologies. So to get us started, just want to make sure that this effort has been completed on a federal highway. I have to put that disclaimer that everything I'm going to speak about is the opinion of, the research team, does not necessarily represent federal highway, and any proprietary product, any ASHE or ASTM standards mentioned here are just for the sake of information. I would like to acknowledge my co-authors or the remaining of the research or the remaining of the working team on this project. Mr. David Johnson, he's my counterpart in the Rocky Mountain area as part of the Asphalt Institute. Dr. Ilker Baz and Dr. Stacy Defenderfer, both from VTRC. Professor Eli Hash from University of Nevada, Reno, and Mr. Tim Aschenbrunner from Federal Highway. If you're wondering what was the initial title of the effort, it's a strategic look at gaps and implementation opportunities for high polymer modified asphalt. This work, you will notice, is based on a lot of input from a lot of people. Acknowledgements go to Asphalt Institute leadership, personnel from New Jersey, Ohio, Oklahoma, Utah, Virginia DOT, as well as Federal Highway Administration, their subject matter experts. So the main question is, we're gonna go back to basics. Why do we modify asphalt with polymers? And then the intention could spin into two routes. Either we're intending to improve rotting resistance, these properties at high temperature, or try and improve cracking resistance. So we're trying to increase that flexibility at intermediate and low temperature. All of that is dependent on the polymer type and the loading level of the polymer into the base binder. A lot of research and practice has been for over 50 years on the use of polymer modified. One of them I would like to mention the work that was completed by the Asphalt Institute back in 2005 by their affiliate committee on quantifying the effects of polymer modified asphalt for reducing pavement distress. It was based on sections that had PMA, whether in their top, intermediate, or base layers, and they were able to prove an extension of at least 10 to 15% in performance life when these are used properly. Now, the question becomes, what makes an asphalt binder a high polymer? And that's a very tricky question because it could be answered from several perspectives. First of all, polymer type makes a huge difference. Second, the polymer content also is a key factor here. And if we compare our typical polymer modified asphalt binders, these are the conventional one that we use on daily basis. These typically are modified with the 3 plus or minus 0.5% polymer. When we start talking about high polymer modified asphalt, these typically evolve about 5, 6, even 7 percent polymer. Like at the beginning, what Nam was talking about, the HIMA sections, they involved HIMA binder that had about 7% of Kraton's SBS polymer there. I want to emphasize, and I'm going to re-mention that towards the end of the presentation, the definition of high polymer is not and should not be based on polymer content, but this is one of the features that could direct towards, characterizing a binder by calling it a high polymer. And the final properties of, the resultant binder, the base binder with the polymer is really dependent on the polymer loading. You'll see you will have an asphalt continuous behavior up to a polymer content of 3%, and that's where the conventional PMA is. You will have a co-continuous behavior between, your base binder and your polymer. And then at the end, once we hit that 5, 6, or 7% polymer, content or loading, that becomes a polymer continuous behavior in the resultant binder. So what we were trying to achieve in this project, there's been a lot of literature, a lot of work has been done by a lot of organizations, including NCAT, including UNR, and many others, even TTI. The intention here is to conduct a gap analysis. This has been in use since 2009. NAM gave an idea about that in the first sections that was paved on the NCAT test track. Now it's time, to take that step back and conduct that gap analysis and try to identify some limitations, gaps, some improvements that could be done, maybe needs. And then we were able to perform that through what we call a SWOT analysis. So the S stands for strengths, the W for weakness, the O for opportunities, and the T for threats. And the easiest way, and for us to have a robust SWOT analysis, we wanted to get that input from states, mainly state DOTs that have used this technology a lot, especially recently, have put it in the field, may have some field data and have a lot of experience. So we can build that based on that input. And I want to mention that also this was conducted to complement the work that was done under Federal Highway Everyday Count TOPS, which is the thin overlay pavement solution. And I know during that NCAT, under leadership of Dr. Vergas, Adriano Vergas of NCAT, and Mr. Jim Musselman, formerly of NCAT, currently of Florida DOT, they did a detailed case study about Florida, since during that time, Florida was the lead state on using high polymer modified mix with their paving program approaching about 5% of, with their HP mixtures approaching about 5% of their paving program. So we wanted to complement that by going to different states, different climatic condition, different maybe need, different material being used, and so on. So you'll see QR codes in that presentation. You can access that tech brief. It's 16 pages that details a lot of the outcomes of this gap analysis. Again, I don't want to spend a lot of time, but there has been a lot of effort done nationally and internationally. I'm just giving an example in New Zealand back in 2010, where High Polymer provided a long-term solution to the frequent major rotting issue that the port of Napier had back in the days, and it delivered really exceptional performance in terms of rotting there. Again, we're taking into consideration this heavy loading. NAM just spent a significant time on elaborating on, the increase in structural capacity when using such type of material. Back during my tenure at the University of Nevada, Reno, we led a research effort for Florida Department of Transportation, trying to give them guidance on what structural layer coefficient they should adopt for high polymer mixes. It turned out to be a 0.54 compared to 0.44 of their conventional PMA. This was performed taking into consideration several, material characteristics, whether aggregate and binder, taking into consideration multiple distresses, taking into consideration various pavement structures, and done based on mechanistic empirical simulation. I'm not going to cover the NCAT test track. NAM covered that in detail. National ones, New York City, First Street in 2012. HP were used there over existing concrete. There was a photo that was published in 2019 by the Transportation Research News that showcased the section being in excellent condition. Oklahoma, I know Nam mentioned that. So they took over the success that happened on the national, on the NCAT test track, and then they took it and then they developed what they call the rich intermediate layer that's being used very frequently with HP binder in Oklahoma. Also, Florida showed interest in potentially doing a binder swap for their open gradient friction course, mixtures. And then they noticed with that binder swap between PMA and HP, they can get about 7 to 8 years extension in the performance life of these type of mixes. And again, QR codes, if you're interested in the details of these studies, you can just scan these QR codes and get the report, download them, and read them. This is as well two documents. The first one is a brief, assessment of all the literature review that's available at the moment. Sorry, that's the second one. And the first one is more of a summary of that, written from Practical Manner as well. These are resources for you to see. For example, the second one documents all the literature review back from 2009 when these things started up to about 2018, 2019 when the paper was published by itself. Now, the main question is the state of practice. Back in 2021, during my tenure with Virginia DOT, we went ahead and we surveyed all state DOTs and trying to see which one have experience with using this type of material. And I want to emphasize these are state DOTs and not local agencies. And during that time, we were able to identify 17 states. It's either they have them in the spec or they have any type of experience in using this type of material. Well, we repeated this as part of this effort in 2025, and that number of 17 went up to 31. And then you'll see various colors. It depends on if the states refer to HP using an AASHTO M320 or an AASHTO M332. So we've seen an interest and continuous increase. We're about 31 states. Now, if we go in 2026, probably we'll get 2, 3 more. Colorado has done a trial. I know Montana, which is here, has done a trial. Arkansas has done a trial, and Missouri is interested in one. So probably we'll pick up about 4 or 5 additional states by end of 2026. And the states where you see yellow stars are the states that were considered lead based on the literature review and that we met with and interviewed to gather that input for the SWOT analysis. They were Utah, Oklahoma, Ohio, Virginia, and New Jersey. So just to give you a little bit about specification here, I'm going to take an example, Utah and Virginia. I'm going to start with Virginia. Virginia use M332 to specify their HP binder. They refer to them as PG76E-28. So they perform their MSCR testing. They have requirement on their JNR being a maximum of 0.1 with a percent recovery of a minimum of 90% at 76 degrees C. The way Virginia handles HP mixtures, they have their typical mix. They just do binder swap. They take their conventional PMA binder out, they put their HP binder in, they pave, nothing else is changed. So this is a way of doing HP mixtures by just binder swapping. Well, in the case of Utah, for example, first of all, they use an M320. Their PG is a 76 minus 34. They only have requirements on their percent recovery, minimum 90 degrees C, minimum 90 percent, and then they have some requirements on additional parameter like delta TC. But Utah doesn't stop here. You can achieve that binder with about 5% polymer, not necessarily the 6 and the 7 like Virginia. Virginia, for you to achieve that binder, you need at least 7, 7.5 polymer. Utah has more a requirement on the mixture, so it's a more of a system for Utah compared to just a binder swap for Virginia. Just to remind you, this is specification for the binder in Utah. Nothing really. Again, I'm repeating myself here. That percent recovery, then everything else remain the same as a typical PG grading following the Astro M320. But what I mentioned, they do have a requirement on their mix specification. They do their end design. You see, they're designing their pavement. Their mixtures down to about 1% air void. They have their requirements on the volumetric properties are different when we start talking about VMA, VFA, even the percent, the binder content, and then they do add a performance, especially at high temperature. I want to mention that the requirement on the Hamburg wheel test, the tracker, the HWTT, has recently been modified. This hasn't been updated in the slide yet, but I believe the 10 millimeter went down to 7, if I'm not mistaken. I need to go and pull the specification again. Again, a lot of lessons learned. They were able to achieve density. It worked for them very well for thick lift. The mix was stable, workable, worked perfectly for them for thin lift, for bridge deck. And then it displayed excellent performance as of today. And then moving into 2025 and 2026, their highly modified asphalt mixture, that system between the enhanced volumetrics and the HP binder, have totally replaced their SMA and with a lot of competitive pricing compared to typical mixture. So it has seen a lot of success. Now I got to move to the other case study, Virginia. In that case, again, they do binder swap. Virginia DOT maintained the third largest U.S. public roadway network. So all the roadways in the Commonwealth of Virginia, except the roads of 2 counties. And ironically, these 2 counties follow VDOT specs. And then if you go on the I-95 or the I-495, these are jointed concrete pavement built back in the 60s and the 50s. So reflective cracking is a big concern for Virginia. So that's when they went and I said, well, maybe we need to invest in that technology and see if we can delay. You will never be able to stop reflective cracking just by laying down asphalt on the top. But if we can delay that reflective cracking. So with using HP, some field data up to 8 years have shown a 34% extension in performance life compared to their PMA. You may say these numbers are small. I just want to remind you, these are 2-inch on top of jointed concrete pavements, and reflective cracking is the critical distress here. And by rule of thumb, this reflective cracking will transfer up to the top by about 1 inch per year. So we got to keep that in mind. Some general lessons to echo what Nam said and what Nathan said at the beginning, always consulting with the supplier regarding any handling instruction. During that time, when we interviewed with the contractors, they mentioned that the recommended time 3 days in terms of tank storage. I know there has been a lot of improvement on binder formulation, and probably we start seeing the number of days in the 2 digits at the moment. Again, contractors would like to do material transfer vehicle to ensure good paving, and they always do checking on the quality of asphalt binder between the tank and also at several interval time, more frequently than conventional binders. The last portion of what I want to talk about, again, if you are interested in learning more about every and each state, these QR codes are yours. To each one, we develop about 15 to 17 page document that showcases everything that went into that state. And then you can learn more about the intention of them using that technology, some of the tonnage, the prices, some of the field performance, research ongoing, things like that, some lessons learned based on that. These are in details, but for the sake of time, we're not going to go into that at the moment. However, what I want to talk about briefly is the SWOT analysis, starting with the strengths. When we developed that, we wanted to split these between people, oriented factors and the technology itself oriented factor. When it comes to people, the support that we get from Federal Highway, this project was a simple example of that, and many others like the EDC6 TOPS that NCAT has led for Florida recently. State DOTs, a lot of interest. We've seen that 17 states becoming 31, and industry and research community, we've seen many of these involved and interested in researching more and even implementing this technology. Technology itself, no brainer. There's plenty of literature that showcase the enhanced performance with using that. Compatibility with the existing design method. Virginia is a simple example of that with the swap binder, and a lot of advancement in binder modification that makes this technology, more available to all states and can be achieved by a numerous supplier. Now, there's nothing wrong in identifying some of the weaknesses that we try to work on and turn these into strengths. Variability and expertise. Of course, not all state DOTs and not all personnel have the same expertise. So that comes with exposure and more training, as well as with the limited contractor familiarity. For the HP technology, lack of standardized definition. I just showed you in that table 5 different specs or 5 different way of specifying HP. So we're going to be aware, and we're going to talk about nomenclature in a second. That's also a big hurdle. We want to make sure when we use a given acronym, we're using that correctly. Higher initial costs, we'll take initial look. That shouldn't be, it's a weakness, shouldn't be a problem because of the increase in performance life or increase in structure capacity. So there are things that can compensate for that. Specification variability, we talked about that. Potential workability concern, just given the relatively higher viscosity of that binder, and some optimization challenge depending on, the availability of the polymer, dosage, and so on. I want to cover the nomenclature. We hear a lot of these acronyms, and standardizing or just making sure we're using the right acronym and the right setup is very important. So I'm gonna start from the bottom right and then go all the way up to the top left. HiMod, that was done by that's the system recommended by UDOT. So it's a big H, small I, big MOD. So that's HiMod, that's the defined. If I go to the middle, HP is a more non-proprietary general nomenclature that has been adopted by the Asphalt Institute, Florida DOT, Virginia DOT, many other state DOTs. If I go to the top right, we're talking about a high polymer modified binder, HiMod. That's a trademarked tech by Kraton Polymer, which falls under the HP, but it requires the use of their specific, polymer structure. If you go down, now we start seeing the high performance grade, HPG, used in state like Texas by TexAPA. And then at the top, we see the big HiMod, all capital letter, or the HMAC, and that's the system that was developed back in France, and that's more of a high modulus asphalt stiffness. It's not necessarily, does not fall under HP. So nomenclature is very important in that case. Again, you'll see increase in initial costs for these states, but all of them were able to justify an extension in performance life and justify, something, a factor to compensate that increase in the initial cost. To finish us up, few opportunities, federal state funding support. For example, this cooperative agreement is a simple example. Growing demand for high-performing pavement. Obviously, we're getting more population, more loads, higher magnitude on the pavement. So we need our pavements to perform better and better. Advancement in testing characterization, which help us, capture the improvement in this material, collaboration, knowledge sharing, and then finally feed performance. Some of these state DOTs have shown that. some threats, supply chain, material availabilities, some budget constraints. Not all states have that flexibility. Workforce training needs, especially with those who lack exposure to such type of material, and state priorities. It could be that some states it's not their priorities to do HP. So with that, I'll give it back to Nathan while we're doing that. Just remember, it's a performance-based approach. It's application-specific use. What happened in a given state, state X, does not have to happen in state Y. We assess what we need, and then we, round the use of that technology towards that. Cost-benefit evaluation is very important, and feedback loop. Just do lab testing, trials, field data, come back, reassess, and then improve from there. Thank you.
Well, yeah, let's go ahead and wind this up and let's get to the Q&A. I know there's already a couple questions in the chat. Y'all feel free to go ahead and drop those in. So yeah, just a summary of recommendations here. Nam talked a lot about how using this type of material you can recalibrate, structural layer coefficients using the ASHTO 93 guide. Really conservatively, we've found that in just a straight binder swap, you can get the structural coefficients 70% higher than conventional asphalt mixes. And if you talk to Surrey and Dr. Tim, they'll tell you that that's probably a conservative estimate, especially as you start thinking more towards what some of these other states are doing and using higher asphalt contents like Utah. I'd imagine those numbers go up even higher. And then obviously the same effect would happen on ME design transfer functions. I would say one of the biggest recommendations here is sometimes we talk about research that has just barely crossed the threshold into ready for implementation. I don't think that this technology would fit in that category. This stuff is ready to go. Johnny talked about 30-something states have at least trialed this type of technology. We have seen from the test track that these high polymer mixes can produce perpetual pavements at 6 inches, maybe I think 5 3/4. I'm not saying you have to be that aggressive, but I do think the technology is there. This is a tool that's ready to be used, and I'm glad that it's getting kind of the airtime that it is. I thought that this was a great point that Nam made that we've done this on the track, and then also Oklahoma has done this in the field, that you can use these mixes without doing full remove and replace of pavements in need of rehabilitation. That is really big. If you can limit the amount of excavation that you have to do underneath, even underneath failed asphalt pavements down into the base, that's significant cost savings. You don't run so much risk of having water, a big rain event move in and flood the work site, and then you have water trapped under there. That's a huge win, is being able to use this technology without having to do full remove and replace. So that's great. If you listen to Johnny talk about this stuff, he talks about definitions in every single one of his presentations. And if somebody is going to talk about something that much, it means it's important. Definitions vary, nomenclature vary, and it is important that we are clear about what we're talking about. Some states have rebranded this for their own specifications, and that's fine. And obviously, there are some trademark names out there, that are kind of synonymous and in our minds a little bit with this technology. But there's also non-proprietary ways of describing this technology. But also binder specs are different, and so that doesn't really fall under definitions. But as you start looking across the states, there's different ways of specifying whether you're using PG grading or masker grading. And it's really important that we kind of pay attention to those details. We talked about this already, but I mean, over 30 states have already gained experience with HP binders. Some have already put it in their specifications. Others are doing trial projects. I'm on the road here in Arkansas, and they've recently done a project here and have found great success to it. And so I like to think of technologies that are like off the shelf ready. I mean, this doesn't require too much to go ahead and start producing. I saw there was a question in the chat, which we'll get to, about plant modifications that need to be made. I think that's a great question. We're going to get there. But for the most part, I mean, this stuff is ready to go. Pay attention to storage, tank storage time. We'll talk about plant modifications here in a minute, and having backup options versus storing long term in the tanks. And I like, sometimes, simple is best, right? Using just basic best practices like material transfer vehicles that's the way to go. And then the last point, I know it's buried here at the bottom of the screen, but I don't want to lose sight of this. I would probably say this is, in my opinion, this is the biggest win for agencies who are considering adopting this technology. Increase in initial costs. Yes, that will happen. Johnny showed a summary of that, looking about maybe 20%. I didn't get a quick average, but that seemed about right, somewhere in that range. But this will equal reduced life cycle costs. Or it could even be offset by change orders that are made, or value added engineering propositions that are added in, because of the opportunity to reduce thicknesses or swap mix types. And there's a famous story going around about what's happened to SMA mixes in Utah, for example. But keep this in mind. I mean, it may cost a little bit more up front, but uh, these pavements, they can become perpetual pavements, and we saw one of them got a perpetual pavement by conversion award. So I'll shut up at that point. I think let's have time for some question and answers.
That sounds awesome, Nathan. Thank you very much, man. That's such a timely topic and really fun to look at. I think one of the first ones I wanted to hit that we saw in here was that, if a contractor is used to running a regular PMA or regular polymer modified asphalt binders, is there any changes that they need to make to their plant and their processes to really get into this higher polymer binder?
Do you want me to take
Yeah.
a stab at that?
Yeah,
Yeah,
Johnny,
Johnny,
go
that'd be
ahead.
great, Johnny.
Sure. When we talk about high polymer modified binder, viscosity is a major component to look at it. I don't like to describe it as a major concern because it's not. So if looking, for example, at some database of viscosity of binders for Virginia DOT, the cutoff limit on the viscosity is like super pave, the 3 pascal second. Theirs is falling at about 4.8. You gotta remember that that is conducted at 135 degrees C or 275 Fahrenheit, which is, in my opinion, way lower and does not represent necessarily that binder. So when we met with the contractors and then talked to them about some hurdles and challenges, first of all, when they're running plant, they don't like to, jack up the temperature. There's always that, leaning to decrease the temperature by 5 or 10 degrees Fahrenheit. In that case, temperature has to remain high. We're talking about anywhere between 325 and 340. I know some states like Florida DOT have a cutoff limit of 340 degrees Fahrenheit on the mixing temperature. Others, you're gonna make sure that your pumps, and then everything has enough diameter to be able to push that material with viscosity. So if typical plant, if I'm not mistaken, have that 2-inch diameter, probably in that case, this needs to be increased to 3 or 4 inch. Given that more recent plants have had that already built in for such technology. So that's just to keep in mind. I recall I was on a job, I'm not going to give more details, and they were not ready to push that binder, and it ended up clogging everything, the whole system. They have to shut down the project for a couple weeks until they figure out something. So, but beside that, your mixing is the same. As long as the binder is at the correct temperature, you can produce that mix hot, get delivered. A lot of states use warm mix additive as well as a compaction aid, as well a mean to, hold that heat while you're holding that mix from the plant to the job site. On the job site, compaction remains the same, effort remains the same. Some contractors gave us some tips that he likes to run a truck or two of a regular non-modified mix just to get everything smooth and running. Then they pick that up and then they start running the HP mixture there. They were able to achieve density, smoothness at the top. So it worked for them, but it came with some experience and exposure. So I'll let Nam interject if he has anything to add.
Johnny, I agree with what you said, and based on the experience that we have at the test track, and Nathan can say that later on too, that there should not much change in terms of production. Now, the only thing is that if you're using very high content of polymer, there'll be a time limit for how long that binder can stay in the tank. And the technical service from asphalt supplier can provide that number to the contractor very easily.
Yeah, I like that. You know, had a great discussion yesterday with the folks at UDOT and some of the work they've done with their high mod mixture. And I want to make sure that I come back to that because the question that was asked about the contractor just says to run high mod. And I'm personally on a crusade for this idea that if we're going to use the term high mod, that it needs to be the whole mixture, not just the binder. And there's a lot of reasons why that whole mixture change needs to happen there. But I also heard that they have some contractors who have found success pumping their PG 76 minus 34 binder in 3-inch pipes on the plant, but using a 4-inch pump. So that's another alternative that's out there that a contractor may want to consider.
Yeah, one more thing, Travis, to add here that the
Yeah,
binder that goes into the high mod mix typically is less viscous than a traditional HP or a high mod trademark binder
yeah,
that uses 7% polymer. So that 2% difference in polymer make a difference. That
yep,
doesn't mean it puts one, more polymer, you get a more enhanced property. You gotta keep in mind that the high mod is successful not because only the binder is at a 5%, 7% should be better, but because you made that changes in the mixtures, the low design air void, the high binder
yes,
content, the low, high density compaction. We're gonna keep that in mind too.
yes, absolutely, absolutely. So, um, one of the other things that I kind of wanted to reiterate and bounce back on there was the thought around binder swapping and finding success in saying, we've got a job that we're running. We don't need the high polymer everywhere, but maybe we're coming up to an intersection where we know is going to have industrial traffic and we want to switch to the high polymer through that intersection. What challenges have you guys seen with that kind of switching and still maintaining the ability to get density and get it to be workable through the equipment? Nathan, no.
Sorry, can you ask that again, Travis? I was having some connection problems.
You bet, you bet. As there was some discussion about swapping binder here. So, I can certainly visualize where an agency or a pavement owner may say, hey, we're paving this job and it's great, but we're coming up to an intersection where we know we're going to see some industrial traffic and that changes the loading condition. Can we hot swap into a high modified or a HIMA binder for that intersection and then switch back? What challenges have you heard of or seen contractors may have as they try to do that kind of a switch and still get it to run through their equipment?
Well, maybe cynically speaking, a lot of contractors just don't want to do that.
Yeah.
But there's nothing stopping you from being able to do that. Uh, I guess the main issue is as you're going to have a train whenever you make that switch in the plant, depending on your plant size and flow and tonnage rate, there's going to be a delay until you actually get into that material. But any good plant operator is going to know exactly what that delay is, because they're probably really good at kind of nailing it right on the head to make sure that they're not wasting any material. Um, but
Yeah.
no, swapping binders is not an issue in general. The only issue I would say on this is it goes back to the viscosity, and you need to, whenever you're running your plant, it's helpful if a lot of them you can actually look at real-time viscosity measurements, and you want to make sure that you're not getting slugging. You can tell just by watching the plant, but as you're making a swap into a more viscous binder, you've got to make sure that you're actually getting good flow. And if that happens, and if it doesn't happen well, you just end up wasting a lot of transition material. So
Hmm.
having the plant hot, and kind of having it primed and ready to go to make that swap, it really just goes down to plant best practices.
Yeah. Yeah. Great. Johnny, you unmuted there. Do you got some input you want to offer?
Yeah, based on my experience, I would say the opposite way. Typically, when contractor bids, they bid on an HP mixture that's already out. And then they typically do binder swap. They just verify the design, but they always work on having a plan B. Back in the time, that 3 days time storage was a little bit hurdle. So if you're doing during a paving season, you're in Northern Virginia, in the Fairfax area, you never know. You have a sunny day and suddenly you get hit by extensive shower and rain. That may delay you. So you want to have a plan B or what you're going to do with that binder if it stays, on site for 2, 3 days and you don't have leeway to pave it. So typically they work more on a plan B or they can dilute that binder and use it elsewhere and then get a new
Yeah.
shipment. So I believe their headache will go into that route more than, okay, if I want to do binder swap, can I do it and pave it? Yes, it's easily done, as long as they have the background on how to do and they're exposed to it. But the other one has happened several times in Virginia, for example.
Yeah.
Johnny, I have a quick question, and then we may wrap up here if there's no more questions. And this is because I'm not as smart about binder as you are. So storage stability on these HP binders, if they're about 3 days, and I know you said technology is getting better, how does that compare to typical polymer modified binders, like your 76 minus 22s?
I personally don't have a response to that. I believe mm, the PMA does not have a limit on storage stability as long as you're maintaining good agitation and whatever other storage requirement compared to HP. But I've heard that now the HP can even last longer. You can even bring down the temperature and ship it across continent and then
Yeah.
re-bring it back up and do so. There is a lot of advancement, but back in the days that was the limitation. But again, we learn, we assess, we improve, we redeploy again, and that's what's happening now with the
Yeah.
with the
I,
polymer world of HP. So
I agree. Not Travis and I were actually talking about that yesterday
Yeah.
about
Yeah.
cooling
Yeah.
down binder and heating it back up, and how does that work for these higher polymer loading rates? Um, all right. Well, with that,
So,
I
so
do
one
want to.
one thing I wanted to throw in there real quick too, and I know that it's something we're saying is that those different levels of polymer loading have that different time that it can be stored. So again, that PG 76 minus 34 that Utah's using, they say that they can get far more storage time on that than they can the stuff that they would specified 7% loading. So Nathan.
yeah, of course. And one last thing, just to not blindside the audience here, we gotta remember that it's not as simple. It's not the same chemical structure of your polymer that you're putting in a base binder at 3.5. You're just ramping that up to 7%. There is a lot more that goes in depth that has to be done on the SBS. If you're using SBS chemical structure to be able to produce HP, they're not the same. I just don't want people to go in their lab. They have some SBS, they start dumping at 7. You will get a piece of a block of coagulated asphalt binder, and you'll be like, "What the heck, Johnny? That's not working." So you got to keep that in mind. That's what make the technology special. Just wanted to highlight that because people think it's just ramping up the polymer content. It's not. It's changing the structure as well.
Yeah.
I often find myself saying, "What the heck, Johnny?" But anyway, hey, thanks again to our presenters. Thank you, Nam. Thank you, Johnny. That was great. You guys are, y'all, as always, top notch in my opinion. So I do want to tell you guys that this was excellent, and I really genuinely appreciate it. Real quick, Chris Peach had just had a comment about refer to your binder suppliers, for storage times and managing binders, and they're going to have the best
Yep,
practices for that.
for
All
sure.
right. Well, Travis, why don't you take us home?
So I do want to let you know that if you'll visit us at our website, ncat.us, that there is a tremendous amount of resources on there. The page that we're showing right here is the test track research. There's the key findings and the synopsis of the last cycle that was run, but you can go back clear to the year 2000 and see the research that NCAT has done and see some of that implementation impact. Always want to invite folks to check out our Training in Your Pocket YouTube channel. Lots of fun 30,000-foot view videos there that talk about different aspects of asphalt pavement testing and asphalt pavement construction. Then for next month on August 20th, we've got another topic that I'm really excited about. That's using BMD trial sections to build agency and industry buy-in. So there are several states that have been building trial projects for balanced mix design mixtures to see how that performance really does work in the field after they verified what they needed to in the laboratory by building sections that they expect to do phenomenal, sections that they expect to do better than standard, and projects they expected to perform as they have for the last 20 years or more. And so we're going to have a couple folks bring that to us and have a great discussion there. So that registration is open. If you see that QR code right there, that will always take you to the next webinar that we have. So again, would like to invite you back on August 20th for the next installation of From Research to Implementation, the webinar series by NCAT. Given that, thank you to our presenters. Thank you, Nathan, for everything.
Thank you.
And we'll see you all next month.